Who doesn't love loggerhead sea turtles? And that's what we're looking at here. These are little turtles that have been satellite tagged, and we can see their journey across the Pacific Ocean.
You know what I love about this data set, kind of cracks me up, is not only is there climatology here, but obviously we see how far they can travel from Japan to California, but the thing that makes me laugh is the larger ones go towards the warmer water, and the little ones are up here kind of hanging out in the chillier water.
Yeah, so the coloring shows the ocean temperature, and we're looking at a year's time, and so we can see the ocean temperatures changing over the course of the year. So I'm Beth Russell.
And I'm Hilary Petticord.
And we're going to talk about the oceans today with SOS Explorer with you.
Yeah, so we're going to go through a bunch of ocean data sets, and by the way, we'd like to do these regularly, so if you have any ideas of what we could name our little show, we could really use some help on that. So we're going from sort of the macroscopic ocean to a little bit more microscopic ocean. This is a really beautiful data set.
So, Hilary, what are we looking at here?
We are actually looking at phytoplankton, but not
So the color's not temperature?
Correct. It's not temperature. I'm not sure if you can see the legend here, but essentially we're looking at lots of different versions of phytoplankton. And but it's obviously modeled in a ocean circulation model. So this is actually the NASA Echo 2 model, and the information for the phytoplankton is actually coming from the MIT Darwin project. And so what we're seeing here is that the larger phytoplankton tend to fight over the nutrient-rich water.
So the cold water.
Yeah, the cold water tends to be more nutrient-rich. So that includes, of course, the kind of Arctic areas as well as the upwelling areas. So we talked about upwelling last time.
We sure did.
But sometimes you get upwelling depending on the circulation near some of the coasts. But then the smaller phytoplankton compete in the warmer, less nutrient-rich water.
Yeah, absolutely. Now, what's moving all of these phytoplankton around?
What do you think?
I mean, it definitely looks like our ocean circulation maps that we have. If you remember last time we looked at ocean temperatures and currents, but we also have maps of ocean circulation, labeling how the oceans are moving, and we can see really clearly here just how much movement is happening in our oceans. The red lines are our warm surface currents, and those blue lines are the cold, deeper currents that are moving along the bottom of the ocean. So we can see there's a lot going on up here. What famous event happened up here?
Oh, the Titanic.
Oh, absolutely. Yep.
Is that what you were thinking?
It was, yes. So the Labrador Current. They think that an iceberg broke off from here, and the Labrador Current brought it down and hit the ship. One theory of where that iceberg came from.
This whole ocean circulation also begins right here. I don't know if you're familiar with the idea of brine rejection, but basically when icebergs form, they only form fresh water. So they actually reject or push out the salt through the bottom of the icebergs, and that really, really salty water in the cold areas is what starts this whole circulation, because it's denser water, it's saltier water. So that's the thermohaline circulation is what this is all about. I've heard that it takes like 1,000 years for a drop of water to actually go all the way through the ocean circulation. So there's a lot of climatology actually that can be done using water, because it does turn over so slowly.
And it's constantly on the move. Now, it's not only ocean circulations that can cause water to move. Another classic example of water moving through the oceans quickly, of course, is tsunamis. So we get an earthquake somewhere underneath the ocean, or a large displacement of rock into the ocean, something that displaces water, and we get a massive tsunami wave.
So it technically could be caused by a landslide, which has happened before in Alaska, like a mountain falling into the water. into the ocean, or a meteorite could actually cause a tsunami. But typically we know of tsunamis because of earthquakes. So this is a really special data set that was made by our friends over at the Pacific Tsunami Warning Center.
Absolutely.
in
They've
Hawaii.
given us a whole bunch of historical tsunamis. We've pulled out the most interesting one, we think, to talk about today. So Hilary, tell us a little bit about this one.
Yeah, so what we're looking at here before we press play is essentially wave amplitude. So all the coasts in the world are blue, indicating that there is no unusual coastal run-up. And then essentially what we're going to see here, this is called the Cascadia tsunami. So that's because it happens in this Cascadia subduction zone. There's actually I think we maybe even talked about Juan de Fuca last time. Did we talk about that? There's a tiny plate here that's actually subducting underneath North America, and it's causing the Cascadia Mountains, which are actually a volcanic mountain range. And we know that there's a possibility for really large earthquakes in that area. So apparently 300 years ago, in 1700, January 27th, I believe, there was an orphan tsunami. There were more people actually in Japan at the time writing things down and keeping records. So what we know of is that there was an orphan tsunami in Japan.
Yeah, so the earthquake happened off the coast of North America, but it was such a big earthquake, 9.2 they think. No one was measuring back then, but 9.2 is the guess. That the wave was so huge, Japan really saw some big impacts. Look at these lines here showing some wave amplitudes that were much higher as they were hitting Japan.
Red is about 3 meters.
Yeah.
That's
So
fun.
normally when you have a tsunami making big impacts on a coastline, the earthquake was close enough that you got a warning. But in this case, Japan was so far away from the earthquake, they had no warning. They just had a tsunami.
Just no idea.
So they called it the orphan tsunami.
And apparently through 300 years later, through some looking at sediments and old trees and tree ring analysis, they found essentially that the trees along the coast of Oregon and Washington and British Columbia had actually drowned that winter, and that they, because you can't really point a date in tree rings, but certainly that winter is when these trees drowned because the coast dropped 36 feet. So that's a pretty intense
And salt water
subduction.
just flooded the forests.
Flooded the forests, and so there were ghost forests all along this coast, which is what
So they were
it
able to
is.
put together ghost forests on one coast, orphan tsunami on another coast, and figure out that there had been a massive tsunami.
Yeah, it's amazing. Science is amazing.
It really is.
My favorite comment from our last live stream was, "She blinded me with science." That was my favorite. So we appreciate you guys tuning in. We're actually playing with our flat screen version of Science on a Sphere called SOS Explorer, which is a product that you can get for your museum or your school. And then, of course, we have our huge round version as well. But we're excited to talk to you about this. So sos.noaa.gov, we have all of our data sets there. You can watch little videos of all of these data sets.
Yeah.
Anything else?
And if you have any requests for future ones, definitely write it on here and we'll see what we can do. Thanks so much, guys.
Thanks. Bye.